Okay, we should be live now. Everyone should be able to hear, and we're good to go. All right. Let's wait for some people to get in here and we can get started. How's everyone doing today? I'm doing pretty good. I have been pretty excited for this. Gonna have to turn my notifications off though, so that no one hears those a bunch of times. Okay, so yes, like I said before, this is the first stream that we're doing officially at Zip Code Wilmington, and we're really excited for this. We hope it goes really well. I hope everyone who has questions is willing to put them in the chat, and we'll try and answer as many as we can. We're talking about a subject that some of you might be somewhat familiar with, but haven't maybe touched stuff like this in a while. We're going to talk about sets today. And I hope that is exciting because I enjoy them. Great. So the first thing we're going to do is we're actually going to talk about what a set is and how it's going to relate to coding and why we use them. And then we're going to talk about their use in mathematics, why they're so important, why they're so great, and we're going to jump into writing some code to manipulate sets and make what we're calling today a set calculator. Great. All right. Cool. So for this, like I said before, we're going to be using Node.js. On my computer, I have Node version 11.13. I don't believe it really will matter that you have the same version, but if you want to be on the same version as me, it's going to be Node version 11.13. For all of the work that we're going to be doing today, I'm going to put it into a folder called Set Playground. And I'm going to be coding in my editor of choice, Sublime. And we'll show the sidebar. All right. So let's get started. I'm going to touch an app file and open it up here. Just to demonstrate how I'll be running code, I'm going to write a simple hello world. and run that over here. The command to run it is going to be node app.js. And you should see here in the console, we get this nice hello world. All right, here's a follow in. Thank you for the follow, Toxic Elitist. Thank you for the follow, everyone who followed yesterday as well. Let's see. Thank you, Combo. Thank you, Angelica Santos. Great. Okay. Cool. Diving in. What is a set? So a set is a type of collection. A collection is just anything that can contain items. But a set is a special type of collection where what we care about is whether or not items are in a set. We don't necessarily care about their order or any special features of particular objects. We generally just care about, is an item in a set or is it not in that set? Sets actually also thus have a uniqueness quality, because it doesn't matter if there's more than one item in a set, we just care about if it's in there the first time. So an example of a set might be something like 1, 2, 3. This set here would basically be a pretty small set. It would be the set containing 1, 2, and 3. So if I wanted to say, is 1 in the set, the answer would be true. All right, that 1 is in fact in this set here. But if I wanted to ask, is the number 9 in the set, that would ultimately come out to false. Now, oftentimes we use sets to talk about numbers and stuff like this, but sets can also contain objects. So if I wanted to have a set of dogs, so I'll have my Rover, my Spot, and I'm blanking on dog names. But how about Rex? There we go. I can have that as well. So in this particular set, I could say, is Rover in the set? And again, same deal, this would return true. And if I said, is Matt in the set, that would be false. Now, in mathematics, sets are really important because oftentimes we can say that we have a set containing things that follow some rule. For example, we can have a set of all even numbers. So I'll have 0, 2, 4, 6, 8, etc., etc. And this would go on for infinity. We would go all the way for our computers until we ran out of memory, but in reality, just until we ran out of the ability to count higher. And once we have a set like that, we can start to apply some rules. So I have a rule that all even numbers are divisible by 2. All right, this is a hard and fast rule. If anyone disagrees with that, we can talk about it, but this is going to be one definition of even numbers. Now, what I can do as a mathematician is I can say, okay, well, I want to talk about maybe something interesting. So I can say I have something like the golden ratio: 1, 1, 2, 3. 5, 8, 5 plus 8 is 13, 13, and then 8 plus 13 is 21. So this is another set that I'm using here. And I noticed something about this set, that every third number in this set is an even number. So I can do something interesting then, and I can say, for a fact, that every third number in the golden ratio is divisible by 2. Now, that might not be a mind-blowing revelation to anybody here, but for mathematicians, that's something that we can usually abuse. We can usually decide that, well, if I have a pattern like that, and I know something about specific sets, then what I want to do is I want to figure out if I can make other sets conform to those. And if I can, then suddenly I know a lot of different things about those sets. So sets wind up being really important to us mathematicians. Sets also happen to be really important to us computer scientists. So much so that the set collection can generally be found in just about every modern web language, including JavaScript. Now, in JavaScript, we can actually just create new sets by calling the new set constructor. So I'm going to do this. I'm going to say set1 equals new set, and then I'm going to add something to this set with set1.add. I'm going to add 1, and then I'm going to add a few more items. Let's add 2, 3, and let's try and add let's try and add 1 again here. And then I am going to print out this set. Save that. I should be able to run this over in my terminal now. And you see that I now get a set here of 1, 2, and 3. Now, one thing to point out here about the way we've coded this. As far as sets work in JavaScript, we'll see that we have the set 1, 2, and 3. Those get added, but then we try to add 1 to the set again. And once we do that, as we expected, because sets have a uniqueness property, 1 is not re-added to the set. And in our result over here, you see 1 in there only once. So that's really cool, and that's really interesting. But now we need to talk about sets and how they relate to each other. Because, like I said before, when we get sets to conform to one another and when we manipulate them, that's where they get really, really powerful. So let's talk about a few definitions. First of all, I'm going to say I have a set here, 1, 2, 3. This is the set 1 that I've just created. A set 1 here has what's called a cardinality, where we talk about the number of items in a set. For this set, we would say that the cardinality of it is equal to 3, because it has 3 items in that set. For other sets, like the set of all even numbers I was talking about earlier, we might say that they have a cardinality of infinity. But it is worth noting that some infinite sets do still have larger cardinalities than one another. But for now, we're just going to talk about finite sets. Now, on top of us being able to talk about a set in its relationship to itself, such as its cardinality, we can also talk about sets in relation to each other. So if I have a set containing 1 and 2, I can see that this set has all of the numbers that are in this set. So 1 and 2 are here, and 1 and 2 are also here. Because of that, I can say that this first set, and I'll call this set A and this set B, I can say that set A is a subset of B. That means that all of the elements in A can be found in B. I can also say that B is a superset of A, in that B contains at least one of every element in A. Now, this is not the only subset of B. We can also have just 1, a set containing only 1. We can have 2 or 3. We can also have any combination of numbers, such as 1 and 3. But we can also have, interestingly enough, all of the numbers from B in A. If this is the case, this is still a subset of B, but A and B being here, 1, 2, and 3, we would say that A is a subset of B and B is a subset of A. This is actually a really interesting property here because we can say that if A is a subset of B and B is a subset of A, then A and B are in fact equal. All right. Next, we're going to talk about the empty set. The empty set is a very special set, and we use it in math a lot. It's one of my favorite things to exploit. It's just a set with nothing in it, as by its name, the empty set. Is that where DOW DuPont is? I don't know what DOW DuPont is, but the DuPont Hotel is here, if that's what you're asking. Greenie 966. The empty set here is actually a subset of everything else. The chemical company, I know the Chemours is here, but I don't know if that's the one you're talking about. I wouldn't be surprised though. Yeah. The empty set is actually a subset of all other sets. When we think about this, sometimes that seems a little bit counterintuitive, but remember I said that a subset just means that all of the elements in the first set are contained in another set. It's not as rural as she says it is. No, it's not that rural around here. I mean, we have code, so that's fun. Great. Okay. Next, we are going to talk about set operations. So sets can operate just like other mathematical objects and things, but we don't do stuff like addition and subtraction like we do on numbers. There are a number of different operations that we can work with. The ones that we're going to talk about today are going to be intersection, union, set difference, or complements, we're going to talk about symmetric difference, Cartesian product, and then lastly, we're going to talk about a special type of set called a power set. So, starting off here, intersection. An intersection of a set is all of the items that are in two different sets. So let's say I have a set A, and this is going to have a bunch of numbers in here. We're going to say maybe 2, 5, 87, and -3. Then we're going to have a set B. Feel free to put in the chat any number that you want me to put in one of these sets, but I'm going to add to this set first 2, and then I'm going to put in 7 and -77, says Krebel. How about 2 more? Let's put in 35 and 12. All right, so we have these two sets. The intersection of these two sets would be all of the numbers that they have in common. So A intersect B would be, let's see, so in A we have 2, and there is in fact 2 in B. Then we have 5, and that's not in B, 87, which is also not in B, and -3, which is also not in B. Therefore, the intersection of these two sets would just be a set containing 2. Now, A couple properties, just to put them out there. The intersection of two sets is always going to be a subset of both of the sets. So if we have something like the intersection of 1, 2, and 3, something like this, the intersection is going to be an empty set, which is a subset of both of them, as I described earlier, the subsets. If there are any shared properties, then the numbers inside of that set, or any object that's inside of that set, is going to be in both of them. So we can always say that anything with an intersect is going to produce a subset, no matter what. It's a very safe operation for that reason. Now, while that's a safe operation, we can also do something called a set union. Now, a set union, so I'm going to say A union B, is always going to be equal to a set containing all of the items in both sets. So for this, we would say that the A union B contains all of the items in A. So this is 2, 5, 87, and -3. And then it also contains all of the items in B. Now, as I've shown here before, B has 2 in it, A also has 2. So we're not going to add that again, we're just going to pass it. We're going to say we have 7, -77, 35, and 12. So this would be the union of A and B. All right. Next, set difference or complements. Now, this is often called set difference. However, many mathematicians choose to use the word complement here because when we say difference, that's usually implying subtraction, and this is not going to be subtraction. So subtraction might be like 4 minus 3 equals 1. We're actually removing some value from this based on what number we put here. Set difference, however, is not actually removing anything. It's just returning a set that has all of the numbers from one that aren't in the other. So A complement B is going to be a set that contains all elements of A that are not in B. So we're going to have a set 5, 87, -3. When we say that we have A complement B, this means that we're going to get a subset of A, because all of the elements here are going to be contained here, but we're actually not going to have a subset of B. We'll actually have a set that contains nothing in B, because that's just the definition of complement. All right. The next one, the symmetric difference, is going to be basically just that, but twice. So the symmetric difference is going to be everything in A that's not in B, and everything in B that's not in A. So just to save a little bit of time, I'm just going to copy-paste a little bit here. This would be the symmetric difference of A and B. Now this one is the first operation that I would say is considered unsafe, because with this operation, what we have here is a set that is neither a subset of A or B. Generally, symmetric differences are kind of cool to look at, but they're not particularly useful because they don't actually give us a subset of any kind. The last two here are something that sometimes people are a little scared of at first, but they are pretty interesting to look at. First of all, the Cartesian product. The Cartesian product is often how we look at multiplication in set theory. However, it's not necessarily multiplication. What a Cartesian product is it's all the possible values of A and B where we get combinations of A and B. So, for A is the set 1, 2, and B is the set red, blue, what we usually mean by this is we get a product that is all the pairs A, B. So A, we have 1 here, and B, red. Now 1 can also be paired with blue, so that would be the next pair that we get in here. we would have the pair 1 blue. And now we've paired all of the items in B with 1, so we'll move on to 2. We get 2 red and 2 blue. So this would be the Cartesian product of A and B, where A is 1, 2, and B is red, blue. This is actually the last thing we're going to talk about when we're working with 2 different sets. And we're going to write a little bit of code that can get us this product, so that we don't necessarily have to do it in our heads. Lastly, we have the power set. Now, the power set's something that all of the zip coders here did on at least one exam, although some of you might have lovingly referred to it as the Leon set. A power set is a set containing all of the subsets of a set. That's a lot to take in. I'll repeat that. A power set is a set of all of the subsets of a set. So, what does that look like? Let's take our set here, 1, 2, and let's figure out what the power set of that looks like. So let's do A is 1, 2. So the power set of A is going to be all of the subsets. So let's think of all those subsets. First of all, we know the empty set is a subset of every set, so that should be in there. Then we know that all of the items individually should be in there. So we have the set containing 1, the set containing 2, and lastly, we know that all of the combinations should be in there. So 1, 2. So this will be the power set of A. All right, we have a set containing sets, and within it we have all of the subsets. All right, am I missing any? If anyone sees that I've missed a subset here, please let me know so that I know to correct this. But I believe this is all of the subsets. All right, great. So I am going to comment this stuff out so that my code will compile. And at the end of the stream, I'm going to put a link to a GitHub repository so that you can all copy this code and read it later. I'll also make that available when we upload this later. But for now, let's get started on writing some code. So before we begin, I am actually going to use a special library here. Now, whenever I code sets in JavaScript, I actually use a library that gives me a little bit more power. The library is called Immutable. If you would like to use Immutable, it's going to be installed using npm install immutable. You can see that down here in my console. I've typed in npm install immutable, and I'm going to run that. And it'll take a minute and install it. Once it does that, I'll come back up here so that everyone can see it. npm install immutable. Once it's done that, I can actually use a set from Immutable. So I'm going to do that. I'm going to put in this line here. It is const set equals require immutable. Now, if you're not super familiar with JavaScript, all I'm basically doing is I'm importing this set module from my node modules folder. If I open my sidebar here, you can see I have my node modules. This folder came in here once I ran that npm install, and I have this immutable package, and within that immutable package, there should be a class within here called set, and I'm just importing that here. All right. Again, link will be in the GitHub repo, and you'll be able to clone this all later. All right. So what I'm going to do here is I'm going to create what I'm calling a set calculator. So in order to do that, I'm actually going to create a class here. I'm going to create a class setCalculator. I'll open that, and inside of here, I'm going to make a function for every single one of the things that we've talked about today. So I'll start with intersection. Intersection is going to take in 2 sets, and then I'll move on to union, complement, symmetric difference, which I'll just call SymDiff in the interest of I don't want to spell symmetric again, because I'm particularly bad at spelling. Cartesian Product, which I'll call CartProd, same reason as before. And then, if we are up to the challenge, we are going to write an algorithm that takes the power set of a set. And we're going to look at what that algorithm might look like. Once we've done that, and we've actually coded all of this stuff, we're going to do some testing on different sets. So I'm going to take a set, I'm going to make a set of, and remember this is the set from Immutable, so you can go use their own Immutable syntax. I'm going to have a set of 1, 2, 3, 4, and then I'll have a set 2, which will be a set of 2, 3, 4, and 5. This will make it easy just to do some testing. Then I'll do my calculator will be equal to a new set calculator. And I will print out calculator dot, some function of set 1 and set 2. And hopefully this is going to print out some calculations that we're expecting. Wonderful. All right, let's jump up here and write our first function here, the intersection. Now, like I said before, the intersection is going to just be all of the items in A that aren't in B. Now, in order to do that then, all I have to do is loop through all of the items in A and see if the item is in B. And if it's not, then I'll want to return that item in a set that I'm returning. So let's first of all create that set that we're returning. We're going to have a variable called the intersection set. And I'm going to set that equal to a new set, and I'm going to make that set immutable, or I'm going to make it mutable so that I can add values to it. So we have a set here, and now I want to loop through all of the items in A. So in JavaScript, typically the way we can do a loop for something like this is we'll use the item.forEach. Again, if you're not super familiar with Node.js or JavaScript, all this is basically doing is it's doing the equivalent of this in Java. For item in A, do something with the item. But we're using JavaScript syntax, so I'm going to say for each item in A, do a function. Now, the test that I'm actually doing here is going to be if B has the item that I'm looking at currently. So I'll do that. I'll say if B has the item, then I want to add it to this intersection set. So what I'll do is I'll say intersection set. Actually, I'll just copy this so I don't have to type it out again. Intersection set dot add. Sorry, no content warnings. Add item. And once I do that, all I have to do then, finally, is return the intersection set. So going over what I just did here, all I did was I created a new set here. Because we're using this immutable library here, I actually do need a mutable set, so I mark it as a mutable. I loop through all of the items in A, and if the item is in B, as well as A, which we know it is because we're looping through A, then all I'm doing is adding that item, and then I'm returning the items once I have completed that loop. So if we test this, we have this intersection here, and I'll go down here and run this function. I'll come back to my handy dandy terminal, and I'll run this app. And I get a little thing here that's kind of complicated to read, so actually I'm going to change this to a string, and I'll run that again. And I get a set 2, 3, 4. Now that's what we were expecting because 2, 3, and 4 here are all in the first set, and they're also in the second set, 2, 3, and 4. The items that aren't shared are 1 and 5, so those are the items that we weren't expecting to be there. Alright, so we got one of these functions down. Let's go on to the next one, the union A and B. Now, a union, like I described below, a union is all of the items in B as well as all of the items in A. So, what I can do for the union is I can loop through A and B and then add all of the items to a set that I'll return. So I'll do the same thing as before. I'll take a union set, and I'll make that equal to a new set, and I'll mark that as immutable, since I want to be able to add things to this. So I'll say var union set equals new set as mutable, and then I'm going to loop through A, the same as before. And remember, this is just the equivalent of like this in Java. We're just looping through all of the items in A. So for each item in A, and now I can do a little bit of awesome JavaScript syntax here. Union set dot add item. Because this is a one-liner here, I actually don't need these braces here. You can add them if you'd like for clarity, but I'm going to omit them so that I can have this be a one-liner here. Then I can actually just do the same stuff here. I can say for each item in B, union set dot add item. Now, if this were a list or an array of some sort, then this code might actually not work because a set needs to have uniqueness. But in JavaScript, as we showed before, if the item is in both A and B, then it won't be added to the union set twice because sets in fact already have this uniqueness quality. So all I have to do here is return the union set, and then I should be good. So we can run this down below. I'll take the union of set 1 and 2, and the result that we should be expecting is 1, 2, 3, 4, and 5, because that's all of the items in both sets. So if I go back to my terminal over here, I'm going to run that node app.js. And in fact, that's the result we see we get. 1, 2, 3, 4, and 5. Moving on here, we have a complement. I have a animal who has decided to come join us. Alright, she should be fine. Alright, we have a complement here. Now, a complement is all of the items in A that are not in B. So actually, we can do something really awesome here. We can actually use a similar piece of code that we've already used up here, this intersection. So I'm going to go ahead and just copy this down here. And I'll just change this name here. I'll call this the complement set. And now, instead of saying I want every item that is in A and B, I can actually just put down here that I want to make sure that all of the items that I'm adding to the complement set are not in B. Because this just has the opposite behavior for that if statement there, I can reasonably expect that if my code worked for the intersection, that the complement should actually work out here. So if I run complement, and again, I'll just go over to my terminal over here and run this app again, I should see that I get set with only containing 1. Now, if I reverse the order of the sets as well, so I'll do set2 and set1, then you should see that I get a set only containing 5. And that's because 5 is the item in set2 that is not contained in set1. Next, we have the symmetric difference. Now, the symmetric difference is all of the items in set A that aren't in set B, and all of the items that aren't in set B that are in set A. So I can start writing some code, but there's something interesting to point out here. All of the items that are in set A that aren't in set B is just the complement of A and B. So I can call this .complement A and B. And this will give me all of the items in A that aren't in B. And I can also call the complement of B and A. And this will give me all of the items in B that aren't in A. Now, if the set I need to return is just both of these sets, then I know that the set I need to return is just the union of both of these sets. So the complement of A and the complement of B, the union of those two things is going to be the symmetric difference. Inverse of the capitalization. So the union of the complement of AB and the complement of BA is going to be the symmetric difference. Just to prove that from before, I have set1 and 2, set2. So set1, set2, complement return 1, set2, set1 return 5. If I do the symmetric difference, then I should expect then to get a result of 1 and 5. I got an error instead. Did I do something wrong? Reference to, oh. I didn't do much wrong, I'm just very silly sometimes. But at the very least, we did get this result that we were expecting, a set containing 1 and 5. Alright, now we're down to the two fun ones. Cartesian product and power set. So, Cartesian product first. The Cartesian product, as I described before, is a set containing all of the pairs of A and B. So, down here, the example I gave before, the set 1, 2 and the set red, blue would give us the Cartesian product of 1 red, 1 blue, 2 red, 2 blue. So let's try and get that functionality. So first of all, I know I need a set to store all of these pairs that I've gotten. So I'm going to create that. And oftentimes we call the Cartesian product the cross product of two sets. So I'm going to create a var cross product. I'm going to say that's equal to a new set, and that set is going to be marked as mutable. Once I'm done with that, I'm going to go through, and I know I want all of the items in A to pair with all of the items in B. So I know I'm going to have to loop through A for each, and I'm going to say the item in A. All right. And so now I have this loop open. I have all the items in A, and I need to pair them with each item in B. So I'm going to have to go ahead and loop through those as well. So for each item in B. Now every item in A is going to loop through every item in B. You might be looking at this and thinking this is probably not a super efficient algorithm. And in all honesty, you're probably correct. However, it's actually really difficult to improve on this because items in A and B don't have order. So if we loop through them separately, it's actually really difficult to predict which items will come out first. So generally when we do an algorithm like this, unless we know something special about the implementation of the sets in that language, this is the best you can do in theory. Now, I don't know anything special about these sets in JavaScript. However, if they do maintain order, then yeah, I would imagine you could improve on this. Because I don't know how to improve on it, I'm not going to today. But if you'd like to look into it yourself, you are more than free to do so. So I have all of these items. What I'm going to do is I'm going to add them to this set that I've created above here as pairs. So I'll say cross product dot add, and then the syntax for pair here is going to be open brackets, A item, comma, B item. And so now this should return pairs for me. If I go back down here and I have my set 1, 2, and I mark my Cartesian product here, I should be able to run this over in my console, and I should see something along the lines of 1, 2, 1, 3, 1, 4, 1, 5, 2, 2, 2, 3, 2, 4, 2, 5, so on and so forth. Here we go, and I get an error again, and I see that I get an error that's a null pointer exception. This is fun. I just forgot to write a return statement. Return that cross product. It is always nicer when you realize that the mistake you made was something like that and not just like something inherent in your code that I have to sit here in silence for like 10 minutes for. So yeah, here we get our cross product that we were expecting. You see we have this 1, 2, 1, 3, 1, 4, 1, 5, 2, 2, 2, 3, 2, 4. Now, I was mentioning before that it's a little bit tricky to do something special like this because we can't really predict order. So, like I'm showing here, 3, 2 came out first. Now, the reason that 3 came first in these for loops, I don't know because I don't know something special about JavaScript. But I'm going to assume that the order that they're sitting in the sets doesn't really make sense to like me as a human. JavaScript doesn't just write the return statement for you? Lame. Yeah, it does. Well, it does, kind of. But I'm using Node.js, and that runtime environment, it will not do that because I have extra lines here. But I believe it would do that if you had just a function with one line. You can go try that on your... If you have Node on your computer right now, you can obviously try that and let me know. But I think it does, actually. Just not for this runtime environment. If anyone else in here is also a Node expert, I certainly am not. Feel free to let me know. But yes, this is the Cartesian product. We're getting a set that contains all of the pairs of all of the items in A and all of the items in B. All right. So lastly, we are going to take on the challenge of the power set. Now, the power set actually turns out to be a really, really challenging problem. For a basic set, a power set can be pretty easy. So for 1, The power set is just going to be a set containing 1, so itself, and the empty set. But then for 1, 2, we already saw up here that the power set is going to be significantly more complicated. We're going to have to have the empty set 1, 2, and 1, 2. Now, if we add 1, 2, 3, and we make this even more complicated, then we're going to have all of these items. We're going to have all these items, but then we're also going to have all of the 2 pairs, so 1, 3, and 2, 3, and then we're also going to have 1, 2, 3. So this ramps up really quickly. For one item, we have two items in the power set. Then for 2 items, we have 4 items in the power set. And then for 3 items, we have 9 items in the power set. You can probably start to see how this is growing exponentially. Not only is it growing exponentially, but the sets themselves get more complicated at every single layer. But there is one great thing that we can exploit here. First of all, we'll also put this down here. The power set of the empty set is a set just containing the empty set. So, what can we exploit about this? Well, we notice that every time we step up, we have all of the elements from the smaller power sets in all of the bigger power sets. So this power set contains the empty set. Well, that one's in here. This power set contains 1 and the empty set, and that is in fact here. And this one contains the empty set 1, 2, and 1, 2, and again, that's here. So we now see that we have something that we can exploit. When you see patterns like this, we know that there is something that we can do with recursion. Now, recursion is a scary word, but we're going to see if we can tackle this today. So what do I mean when I say we can do this recursively? Well, I know that if I have 1, 2, 3 here, then the power set of 1, 2, 3 is going to be the power set of 1, 2, and 1, 3, and 1, 2, 3, which means that I can add 1, 2, 3 to its own power set. Then I can take the power set of all of its subsets. So let's look at what that might look like in code. First of all, I am going to have a set that I need to return. So let's just call this, for now, my current set. So var current set equals new set, and this is going to be a mutable. And now I want to say that if A is inside of the current set, then I should be done. So I'll put that in there. Ergo, if I have a set that contains itself, there should be no subsets of that left. So if current set dot has A, then all I need to do is return the current set. So this is for the base case, basically. This is for the case where I have an empty set, and all that's going to be inside of it is an empty set. Now, if this isn't true, then it means that I'm going to have to do something. It means that I'm going to have to split up this set a little bit. So I'm going to say, for each item in A, same syntax as before, for each item in A, I'm going to create a new set B. And B is going to be all of the items in A except for the item that I'm currently on. So we're going to do A dot, and now I'm going to do a little bit of magic from this set module that I'm using here. I'm going to say A dot filter I such that I does not equal the item. So just to quickly explain what this code here is doing, all this is saying is B is going to be all of the items in A, but before you return it, just filter out every item that's equal to the item that I have up here. So I'm going to get A with everything except for this one item in particular. Next, what I want to do is I want to say, okay, well, I've already determined that the power set of A is going to be the power set of all of these subsets. So what I want to do is I want to take the power set of B, this subset of A, and then for each of those, and I'll say this is the inner set, or I should capitalize this for clarity. For each of those inner sets, I'm going to add that to the current set. So this is going to add all of the power set of B into my current set. And I know this because my expertly written power set method here, the one here that I'm calling recursively, in the end is going to be able to get me a power set. But I'm kind of a little bit stuck now, because if this is the current set here, and all I'm doing is I'm adding to the current set, well, then once I pass in B here, then this current set is going to be empty. So it's not really going to be particularly useful because I'm not keeping track of all of the items between calls. Well, it turns out that there is a way to fix this pretty easily. And the way we can fix this to keep track of stuff between calls is I can pass in this current set as a variable. So I'm going to put this variable up here as an argument, and I'm going to say current set by default is going to be this new set that's mutable, and then when I use this logic, this will actually be maintained between method calls. So eventually I'll be able to come to the end of my recursive calls. And for this power set of B, I'm going to pass in the current set so that it's being kept track of in the recursive calls as well. Once I do that, I'm going to add my semicolons. Once I do that, I should get to the bottom, and all I need to do is add A to the current set. And then I return current set, and I should be good to go. Current set is not a function. I should be good to go. There is, however, one last issue with this. That issue is that we don't have anything that will initially pass this test. The reason we don't have anything that will pass this test initially, sorry, I'm jumping around a bunch. We don't have anything that will pass this test initially is because there's nothing in current set by default. And because there's nothing in current set by default, there's nothing here that by default will escape this. So we're always going to jump into these recursive calls. So we need to think of something that will be inside of every single power set. Well, if we're looking back down here, recall that I was mentioning earlier that the empty set, this very special set that I love ever so much, this empty set is going to be in every single power set. No matter what set I have, the empty set is a subset of every set. Awesome! Yes, the universal case. So, what I can do is I can say by default, this is going to be a set of a new set. And now suddenly I have the default case, and this is universal. All subsets will have this. I'll still make this mutable just in case I need to add more sets, but once I have the empty set, then my current set should already have this, and it will end the operation. So here I now have a function that should give me the power set of a set. So I have my set calculator here. I'm ready to go. Let's start off let's start off easy. Let's actually do something here. So I'll say set3 equals set dot of, and I'll just pass in 1. Because the power set of just 1 is easy for us to calculate, I assume. So we'll do the power set of set3. I'll come back over to my terminal, and I'm going to run this. And I get an error. Let's see what my error was. I see that the error is syntax, unexpected token. Oh, I see. Forgot to comment these out here. Let's run this again. All right, and I get exactly what I was expecting. The power set of the set containing 1 is going to contain the empty set, and it's going to contain the set containing 1. All right, that's easy. Let's add a few more numbers. Let's add 1, 2, 3, 4. All right. Now, I said this scales exponentially before, so we know that this should be 4 squared. There should be 16 items in my power set. So let's see what that looks like. And there we go. This is a little bit chunkier this time. All right, we have 1, 2, 3. We have 2, 3, 4. We have 2, 1, 2, 4. All right, you'll notice these are in no particular order, as I was saying before. Sets don't really keep any particular order, so these are seemingly random. I'm going to assume there is some order because of JavaScript, but they're not really going to be something that makes sense to a human. Either way, this is what this looks like. Let's put in a bunch more things. Let's put in some strings now. Let's say this is hello. And then let's add some more stuff. Someone can give me some words in the chat if you'd like to suggest any. I'm going to put in recurse. I don't know how to spell recursion suddenly. Then parabola. That's a good word. Parabola. Let's put in dog because I like dogs. Let's put in Nova because that's the name of my cat, and I love Nova very much. And then how about zip code rocks? That is a self-plug of sorts. The infamous pineapple returns. I don't know what I was expecting. Okay. Let's put in iPhone. All right. Let's see if we can get the power set of all of these items. Now, I said before, this is exponential here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 items. We have 10 items in our set, which means that we should get a power set that contains 100 items. Let's see if that can run. Oh, it worked! I kind of don't know if I was expecting it to work, but let's paste this over here so we can see it. Yeah, this is the power set of the set that we've just created here. This set here contains all subsets of the set, including the empty set. There it is, the empty set, my favorite set. All right, so this has been a set calculator. I hope that everyone here has enjoyed running through some code. And I'm willing to take some questions until we're ready to wrap up here. Again, thank you everyone for following. I missed a few. Alec Celius, Reese Watson, thank you for following so much. We appreciate it. Oh, Toxic Elitist, I think I missed you before, but thank you. Thank you so much. Can you do that non-recursively? Yes, you can do this non-recursively. So there's a bunch of different algorithms. I'm not going to write them down because we are sitting over an hour here. but I'll just run through kind of what those look like. First of all, there's the brute force method. So basically the brute force method is decide, okay, how many items are in my set? So let's say, first of all, there are 6 items in the set. Well, what I can do then is I can start at the beginning, and I can say, okay, use this number, and then get me all of the items in the set until I have 6 items. All right? And then I have this. Now, there's no more combinations of 6, so what I'm going to do is I'm going to move on. I'm going to say, okay, what's the next set? So I'll say all the items, all right, until I have 5 items, all right? So we're getting all the combinations of 5 now. Now I have 5 items here, so what I'm going to do now that I have 5 items is I'm going to say, okay, well, there are other combinations. So what I'm going to do is I'm going to include the last item and omit all of the other items first. So I have 1, 2, 3, 4 because I'm omitting this first one, and then I'm going to add 5. And then I'm going to have 0, 2, 3, 4, and have 5 because now this time I'm omitting 1. So on and so forth, and I'm just going to keep omitting one character at a time. So this one will take 6 times. This one will take 6 to the 0, and then this is going to be like 6 to the half, and then we're going to do this again. We're going to do it for 4, so we'll have 0, 1, 2, 3. This is 4 items. And now we're going to omit 1 at a time. So we'll have 1, 2, 3, 4, and then 1, 2, 3, 4, 5. Or, yeah, 1, 2, 3, 5. That's it. And we're just going to keep on doing this. And you can see how this takes a very, 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 very long time. So this is not one of the recommended ways of doing this. There is another way that's not so brute force, though. That you can use. However, it only works if your set has order, which we didn't guarantee here. So the way we can do this, if we have a bunch of numbers. So this time let's do 1, 2, 3. So we have a set containing 3 objects. All right. What you can do is you can actually count in binary until you've reached a number of 1s equal to the number of items you have. So what that looks like is this is 0 in binary, this is 1 in binary, this is 2 in binary, and then I just keep going from here. So this is 4, this is 5, this is 6, and this is 7, all right? So this is all the possible numbers you can count in binary with 3 digits here. And then what you do is you go through these and you create a new list. And you say, okay, for every single one of the items in the list, I'm going to create a set. And if the first item in the number here is 0, then I'm going to omit the first item in the original set. All right, so in the first one, I get an empty set because all 3 of the numbers are 0. In the second item here, I have 0, 0, 1. So I omit the first item and the second item, and then I include the third one here. So I'm going to have a set containing just 3. In the second one, I have a set just containing 2, and in the third one here, I have a set containing 2 and 3. And so I keep on doing that, and eventually I get the power set. Now this algorithm here actually is more efficient than the other one, but it's still not actually as efficient as the recursive algorithm that we've actually written above. That being said, JavaScript is not very good at recursion, which might be why you asked for this in the first place. So this might still actually be a better algorithm. However, if you were working in something like Erlang that does a really good job of tail call recursion, then this might actually be not as good of a way of doing it. Yeah, no problem. That was 2 more ways of doing this algorithm. This is actually one of my favorite things here. This actually works for all permutation problems. This is one of my favorite ways to solve a lot of different problems in computer science. One problem that you might have seen before, let's say you have a phone number like 555-2376, right? The problem might be like, give me every single word that you could get on a number pad using this phone number, right? So if I look at a number pad, I haven't looked at a number pad in a little while here. So I want to pull one up on screen. This is one on eBay. This is a number pad here, right? So we have A, B, C, D, E, F, J, K, L. So like one word we could spell with this would be like J, K, L, and let's see, 2 maps to A, 3 maps to D, 7 is P, and 6 is N. Yeah. So this is like the phone number problem. So this would be one string that can result in this, but we could also change the combinations here, right? So this could be JJK, 8APN. This would also be another string that you can get out of this number here. The binary problem that I have here, or this binary solution, is also a solution to this phone number problem. So be on the lookout for things like that. Yeah. All right. We'll take any other questions. We have. Oh yeah. By the way, thank you all for watching this. I know this is not the coolest way to spend a night, but I'm having a lot of fun. I hope you are having just as much fun. I hope you're learning a bunch about sets. This is also not super computer science related, but yeah. Will there be more? I hope there will be more. I think there's going to be more if y'all request it. And if you have requests for other topics to cover, there will definitely be more. We're hoping to do this every Wednesday around the same time, but if different times work for people, just be sure to let us know. Like we said, this is still all very, very new. Yeah, no problem. Thank you. Thank you all so much for being here. All right, I'm going to assume there's no more questions at this point. We'll link everyone to the VOD. Yep, we'll link everyone to the VOD. We'll upload this to YouTube later. And I will give everyone the link to a GitHub repo where you can review some of this code. Yeah, thank you. Thank you, Reese, for being here. Thank you, Alec, for being here. And I'll see you all next week, hopefully. All right, enjoy the rest of your Wednesday. Enjoy the rest of your week. Goodbye.